And the first one, I'm like, yeah.
So guys, how did we do? Was it okay?
That's fine.
Yeah, the way to do those bit strings, those bit string problems with zeros and ones is you sort of look at how are you going to start that string, right? Is it going to start with a 0 or a 1 or whatever? Well, this was just taking that and turning it into monominos and triomino, right? And you can either start with a monomino or you can start with a triomino, right? It's just that they take up different amounts of space. So what you should have for HN is either that you started with a monomino, which would mean that the remainder of what space you have left is n minus 1 spaces, right? Or you started with a triomino, right? In which case you would have had h sub n minus 3, but if you start with a triomino, you can't have another triomino. So it has to be a triomino followed by a monomino. That actually takes up a total of 4 spaces. This is H4. I'm scaring everybody. Scaring everybody. Yeah. It's something like this, where it's a physical problem. Please try to use, please try to use initial conditions that are actually real world sensible. I would not have used H0. It would be better to use H1 through H4. And I need 4 initial conditions because the relation is a 4th order recurrence relation, right? Yeah.
Why is monomial H sub n minus 1 then not H sub n minus 1?
Well, because if I start with a monomino here, then I'm allowed to do anything I want in these remaining n minus 1 slots, because it doesn't say that you can't have consecutive monominos. The question just said you can't have consecutive, pardon me? No, it's just the triominoes can't be consecutive. Yeah, so it's always the reading of the question is always the first battle. But you either have that or you have a triomino followed by a monomino, in which case you have n minus 1 bases. Okay, so then you just have to figure out the initial conditions here, right? I was glancing at the answers people were turning in, and not too many of them looked. I don't think I saw the same answer twice. So somehow, somehow lots of people came up with lots of different things. So like H1, like if I have a 1x1 board, there's only one thing I can do, just put a monomino there. If I have only a 2x2 or a 1x2 board, I still can't use the triomino, so I have to use 2 monominos. That's only one way to do that, right? As soon as I get to a 1x3 board, now I could do 3 monominos or 1 triomino. And so that would be 2 ways to do that one, right? And then if I have 4 spaces, well, I could do 4 monominos, or I could do a triomino and 1 monomino, or I could do 1 monomino and a triomino. So that's actually 3 from there. And then all you have to do from here then is just use this relation, figure out what's H5, H6, H7, H8, and H9. Just by using this formula here, you can get it from there. So I forget what the actual answer is.
Now I guess more.
14? Okay. Yes.
Initial conditions, like different permutations do matter of like, so like H4, it does matter that like the mono and then the tri.
Guys, please.
Does my question make sense? Like it matters like the permutations
The
of.
orders in which things are sitting does make a big
Okay,
difference.
so that
Yes,
does.
that is very true. So
Okay.
like, that's why these are not the same at all.
Yeah.
Exactly. Okay, and then the graph theory problem, did everybody find the Hamilton cycle?
Yeah.
There was one there. It's a little tricky, but it's there. And that was the only thing I had. I don't think it had anything else. So that was that. And then the third problem is kind of a standard one. Graph isomorphisms preserve structural properties. So you'll see that in the sample test, I think I ask you to prove that if G1 is a tree and it's isomorphic to G2, then G2 is a tree. If G1 is connected, then G2 would be connected. If G1 is planar, G2 would be planar, like all those, any property, just pick your favorite property and you can prove that it's preserved by an isomorph. I picked a 5-side one for the quiz just because it's relatively doesn't take too long to write it all out, but that kind of spirit of a question is something you want to practice a little. Back to it. Okay, so my plan is to grade these like ASAP. If I can get them, it depends on how busy my office hours are, but if I can get them done by tonight, I will. I was trying to think about how to get these back to you, which is going to be a little tricky. I suppose what I can do, I could take pictures of each of your graded exams and then email all of you one by one with your results, so you don't have to pick them up. If anybody happens to be around tomorrow, I could probably, if you happen to be on, I know it's Friday, not many people are going to be here, I could probably pass them to you that way. I will post the solutions into Canvas though, but I'll try to get them up ASAP. And then if you really want to get your exam back, let me know like when you're going to be around. I'll do my best. I don't think I'm allowed to just like set them out for people to come pick them up. So anyway, I think I'll hold on to them until I am able to give them back to you. Okay. All right. So let's get started. I made a decision, and I'm sure you're all going to put this in your SOQs that I'm like the nicest professor you've ever had, because I have decided to nix this homework assignment. Because I am basically going to do it with you today. We're going to more or less work through it as kind of part of a review for the exam. So I will also post the solutions and so on and so forth. One of the questions doesn't even make sense. It says show that the graph on problem 2 is not planar. Well, that was from an old quiz, so that one would have had to have been changed anyway. This graph was on your quiz. That's right. That's right. So anyway, I'm going to do some of these with you just now. And so we'll work on the homework. We're also going to work maybe a little more on the group work that we didn't have probably time to totally finish last time. And so that's my plan for today. Don't forget that we do not have class on Tuesday. So on Tuesday, you can focus on your studying. I am going to be around through Saturday. So I'm here today, I'm here tomorrow, and I'm here Saturday. If you want to see me face to face at my office or in Zoom, you can do that through Saturday. Starting on Sunday, all the way through Thursday, obviously for your exam next week, you'll have to be working with me through Zoom. In the midterm resources folder, I have the review packet with my Zoom office hours. And remember that they are different than my normal hours that I have weekly, because I'm going to be in a different time zone. So be sure to look those up. I don't have them off the top of my head right now, but they're written out. If I need to change anything on those, I will email you. I should have pretty good internet access all the way through next Thursday, I'm pretty sure. And Thursday we will take the test. The exam, of course, we start at 4 o'clock. I will probably ask my proctor to give you a little bit of extra time at the end. I'm also debating whether to have you guys, you might bring a phone next Thursday. You're not going to use the phone during the exam, but at the end of the exam, I'm trying to think about how to get these graded more quickly than having to wait till I come back, which is like 2 weeks from now. So one way to do it would be to have you, just before you turn it in, take pictures of your stuff and then put it into Canvas. But that takes a few extra minutes. So I would recommend, if you have some big plans next Thursday, try not to have them right at 5:15 or whatever. Give yourself, I'll probably give you an extra 10 minutes to work. I'll ask my proctor to do that. And then maybe a couple extra minutes to take pictures and so on. So just try not to be, if you have some exciting date or something, next Thursday would maybe not be the day to do it unless you're going to do it later. So you have plenty of time to get everything done. Anyway, that's just my advice. Are there any questions about any of that? Jose?
I would just suggest we get, Western about this, you have to start from Dropbox, where we just scan it and then upload it here.
I don't need to use Dropbox. I can just use Canvas.
Well, then,
Yeah, I think that'll be fine. Yeah. Yeah, I should have some internet access. So if the reason to have you scan it into Canvas is then I can be grading them while I'm gone. And then, Because otherwise, I'm only coming back like literally like a day before we start back up after the break. So that means I'm gonna be like, and I'm gonna be totally jet lagged and exhausted. Presumably, I will have just come down from 20,000 feet, so my brain won't even be working. So trying to grade the exams might be a little interesting. Anyway, yeah, so we'll see what happens with that. So just bring a cell phone in case I decide to do it that way. I've got to think of that through a little bit more still. Okay, so with that in mind, I have put a bit of a recap over here on the board. Just want to remind you where we kind of left off. This is the only sort of new section 12.2 that was not covered by the quiz, but which will be on the exam. So this material about planar graphs. So let me slip this over this way for a minute. So remember that if we have a connected planar graph, then that graph will split the plane into regions. And the number of regions is little r, the number of edges is e, and the number of vertices is n. And we proved on Tuesday that that expression r minus e plus n always adds up to 2 for a connected planar graph. Pretty neat, right? So you first prove it for a tree, then you take whatever your graph is and you find a spanning tree for it, and then you sort of inductively add edges to that spanning tree, all the while preserving this relation. Kind of how that works. And using this Euler theorem, we proved in class on Tuesday that there's an upper bound on how many edges you can have in a planar graph. So if I have a graph that's a connected planar graph, the number of edges can never be more than 3n minus 6. So it's less than or equal to 3n minus 6. And we proved that by using the Euler theorem here, along with kind of the handshaking theorem for the degrees of regions. If, in addition, your graph does not have any 3 cycles in it, so if you look at the graph and say, oh, there's no 3 cycles there, then we can actually get a stronger statement, which is that the number of edges is even more constrained by a sharper upper bound, right? 2n minus 4 is going to be smaller than 3n minus 6. But that requires there to be no 3 cycles in the graph. Okay, this was in the group work, which I think most people did have a chance on Tuesday to work with their groups on that. It's essentially the same proof, just with a slight tweak to the proof itself. And then I'm not sure if people got to this other, sorry, Nikolai?
If a graph is connected, does that mean that these 2 vertices? Or like?
We may as well assume that. If there's only one vertex on the graph, the graph theory portion of this course would be about 2 minutes. So let's assume that there's at least 2 vertices. Yeah. I'm not sure if everybody got to this this third fact here. This was also on the group work, which is if you have no 3 cycles and you also don't have any 4 cycles, so the smallest length cycle that your graph has is a 5 cycle, then we have an even sharper bound, which is that the number of edges is less than or equal to 5/3 of n minus 10/3, okay? So of course, this will be applicable to far fewer graphs because there's not as many graphs that are going to avoid having 3 cycles and 4 cycles. But if we happen to have a graph that does not have, by inspection, does not have any 3 cycles or 4 cycles in them, then we can really tighten down the number of edges that we maximally could have if the graph was going to be planar. These facts, of course, are primarily used to disprove that your G is planar. We can disprove it, right, by using 1 or more of these facts, right? And of course, we could extend it to no 3 cycles, 4 cycles, or 5 cycles. I would recommend that you be familiar with how these are proved, because they're all proved the same way. And so you've really sort of seen it 3 times already right here. And so I wouldn't be hesitant at all to ask you to sort of explain that same kind of argument again. It's definitely something worth a few minutes of your time as you're studying here. Fernando.
Why do we have like I know like when we do the proof, we typically just change some number, like was it 3R?
Mhm.
So 4R, why don't we just like have like a general AR?
Oh, we could. Yeah, we could. What's that?
And then we just swap it for whatever K is.
Yeah, we certainly could do that. Yeah, maybe you could write up a formula for me. So he wants to say, suppose the graph has no 3 cycles, 4 cycles, 5 cycles, up through K cycles. Right? If you don't have any of those, then what would be the edge bound in terms of K? And you could do that. You absolutely could derive that. So maybe that's a good test question. Who knows? No, I just. So. Just getting me quiet. Sorry, I'm not quite ready for that yet. I want to do a couple of the problems from this homework assignment. So I'm going to start with 26 and 27 from the homework that I have now canceled. So let's just do this as an example. So what it says here is, we'll just kind of think of this as a warm-up. Let G be a planar graph of order n. Okay, so n vertices as usual, in which every vertex has degree k. So this is a graph where all of the vertices have the same degree, okay? And it's just k. And what I'm going to do here, guys, this is a nice little exercise. I'm going to try to prove that k is less than or equal to 5. I'll try to prove that k is less than or equal to 5. All right. So the first thing is that it would make the most sense to try to use some of the stuff over here. But of course, you'll notice that absolutely everything on this board requires the graph to be planar and connected specifically. This does not say that the graph is connected. But the idea, of course, is that the assumption that's given to us, that every vertex has the same degree, would apply to each component, each connected component of the graph. And so if you could just focus on one component only, right, then it's almost, it suffices to prove this for a connected component of the graph, right? So we may assume G is connected. And I'll just to explain why we are assuming that just so freely is this is just by considering a connected component of G. It's just a minor point, but you know, when we're using these facts, of course, we want to make sure that the assumptions are going to be true. So we have a graph that's already planar, and now we may assume that it's connected. We're basically just going to focus on one connected component, right? If every vertex of the whole graph has degree k, that would include every vertex of one of its components. And if G was connected to begin with, well, that component would be the whole graph, right? There'd be nothing else to worry about here. Okay, so we have all of this stuff over here available to us. We don't know anything about 3 cycles or 4 cycles, so I'm guessing that facts 2 and 3 are probably not going to be helpful to us because, I mean, unless we try to do some kind of cases, but that's really not going to be necessary here. So we can certainly focus though on the first fact, right? So from fact 1. Okay, I'm trying to just approach this like, how would I do this problem, right? And just, I would think about this fact, and I know that the number of edges is less than or equal to 3n minus 6. Is there some way to connect edges, or is there some way to associate edges with degrees of vertices? Because this question is assuming something about the degrees of the vertices. Oh, we have the handshaking theorem, right? That handshaking theorem is really helpful. So let's just also recall the handshaking theorem. Let's write that down as well. So the handshaking theorem, if you remember what that said was that if we add up the degrees of all the vertices, we would get 2 times the number of edges. That's the handshaking theorem. And every vertex has degree k. And how many vertices are there? n of them, right? So it's just k plus k plus k plus k n times, that's nk. So in other words, this is just nk equals 2e. Right, so I could feed that in to this inequality somehow then, right? Could just go ahead and put that in there. So where I see the e, for example, and here I also have an e, let's put those two boxes together and just see what comes out of it, right? So if I put these two boxes together, does that sound like a plan?
Yeah.
Okay, so on the left side, I'm gonna have nk over 2. And on the right-hand side, I have less than or equal to 3n minus 6. So we can just kind of do that. And I would like to solve for k, because this is what I'm trying to prove here. So if I solve for k, that means I need to, what, flip this thing over, multiply through by 2 over n. So that's going to be 6 minus 12 over n. If I clean that up algebraically a little bit. And of course, k cannot be a fraction. The degree of a vertex is going to be a whole number. And it's clearly a whole number that is strictly less than 6, right? If you're taking something away from 6 here. And so, well, that pretty much proves if k is less than 6, doesn't that prove that k is less than or equal to 5? It's a whole number. It can't be anything else. All right, so thus k is less than or equal to 5. Kind of a nice little problem. So we can actually prove that in a planar graph, you can't have a lot of vertices of high degree. Of course, that would imply lots of edges. Lots of edges is always bad when you're thinking about a graph being planar. Okay, everybody comfortable with that one? Make sense? Okay, let me just mute that screen for a second. I'm going to come back to it in a minute. But for the moment, let me give myself a little room here to do number 27, the very next problem that was originally on this homework. And this is a similar kind of problem. I'll write it up and then we'll just kind of solve it together, right? See if we can figure this out. So this one just says, let G be a planar graph of order n. And this will be n greater than or equal to 2. Okay, so n is at least 2. And then what it's going to ask us this time is it says prove that G has at least 2 vertices whose degrees are at most 5. You know, I think I had to read this about 4 times to understand it. You have at least, you have at most. It's like, what the heck is this saying? The logic of it is a little bit fuzzy. So there has to be at least 2 vertices whose degree is limited. Has an upper bound on it. Okay, so it has to be at least 2 of those. I think the best way to understand the question in terms of just even the logic of it is to imagine by way of contradiction that this is not true. And what would that mean, right? So by way of contradiction, what we could do is we could assume that if there are not at least 2 vertices, let's get the logic straight. If there are not at least 2 vertices whose degrees are at most 5, doesn't that mean that they're assume that there is at most 1 vertex whose degree is at most 5. Instead of at least 2 of them, well, there's at most 1 of them that has that property. So instead of having at least 2 vertices with whatever the condition is, by way of contradiction, assume that there is at most 1 vertex whose degree is at most 5. Another way of saying that is that at least n minus 1 of the vertices has degree at least 6. Okay, let's write that down. That is at least n minus 1 vertices has degree at least 6. So all but one. All but one. You cannot have 2 vertices of degree 6 or more. There's yeah, there's maybe one vertex that could have degree less than 6. All of the others have degree at least 6. Make sense? And see, something like that would be true on each connected component again. Right? So all but one of the vertices, right, has to satisfy this condition. And that would be true even in any given connected component. There's one outlier. There's one vertex that might have a low degree, right? At most one. There's at most one vertex that would have a low degree. It's kind of what I said, the way I phrased it originally. So that would be true if I look at a particular connected component of G, right? Within that component, there could be at most one vertex of low degree, because if there were 2 vertices of low degree in one of the components, well, then the whole graph already has 2 vertices of low degree. So that we may again assume, so again, like the previous problem, we may assume that G is connected. If I was going to put this on the test, I probably would just assume that G is connected to begin with. I should just make it as an assumption. That'd be easier for a test question. Question, Julie? That's right. Yeah. So there's at most one vertex whose degree is small. So that could be either 0 vertices or 1 vertex. And so the complement of that is that either n minus 1 or n of the vertices have degree that's big, right? So let's do our, since we're talking about degrees of vertices, let's do our handshaking theorem again. So again, so 2e is equal to the summation of the degree of v, where v is a vertex, from the vertex set. So it's same handshaking theorem again. And this time, what did we say? At least n minus 1 of these numbers is at least 6. So this is at least 6 times n minus 1. In fact, you probably could make the case that that's a strict inequality, because there is one other vertex that, assuming the graph is connected, every vertex has to have a degree of at least 1. So there would at least be one more to add to this, but we're not even gonna need that. We're not even gonna need that. Let's just divide through by 2 here. Okay, so then if I divide through by 2, E is greater than or equal to 3 times the quantity n minus 1, which, by the way, that is just 3n minus 3. Anybody seeing the contradiction yet? Let me write it a different way. 3n minus 3 is less than or equal to E. Well, then what else do we know that we haven't used yet?
No order.
Fact 1. Fact 1 says E needs to be less than or equal to 3n minus 6. Does anybody see any problem here? I certainly do. This number here is bigger than this number here, right? If you subtract 3, it's going to give you something that should be bigger than what you would get if you subtracted 6. So this is totally backwards. This is like totally, inequalities aren't even making any sense here. This is a contradiction. Contradiction. Okay, so that kind of takes care of that. That takes care of that. Okay, so a couple nice problems here from the homework having to do with the handshaking theorem together with, I guess it was fact 1 primarily. Okay. I haven't written the test yet, but I mean, you put yourself in my shoes. I like these kinds of problems, connecting these ideas together. Like, what could I do on the exam? I said, I wonder what this problem how it would change if I did exactly the same 2 questions, but I said that also G has no 3 cycles. Because then instead of using fact one, I could use fact two and kind of try to run through something similar to that. That's the sort of thing, if you're studying for the exam, I would recommend just playing with something like that. And take a question that you've already done and just tweak it a little bit and just see what comes out of it. I haven't even done it. I'm just thinking out loud. Yeah, stream of consciousness off the top of my head. Okay, good, so far so good? Nice. Okay, there was something in the group work. Does everybody have a copy of the group work, by the way, that we were looking at on Tuesday? I do have extras here. If anybody might need one, is there anybody else who could? I've got quite a few. I keep overestimating how many people are actually enrolled in this class.
Yeah, I might need a new one.
You need one too? Okay, that's no worry. Anybody else back here? missing that? This is number 11. Group work 11, that you can look on with a partner too if you want it.
I'll take a look at it. Oh,
Okay, I got an extra. Anybody else need one?
you know what you should do? You know how when you take the hiking, there's like a trail like that.
Yeah,
You should make one.
I should think of something like that. That's a good
I'm
idea.
going hiking.
Be careful what you wish for. Okay, so I just wanted to talk about this crossing number idea, which is sort of generalizing the idea of a planar graph. So just gonna make you can put this into your notes if you want to, or you can just reference to the group work that I just passed out. But given a graph G, right, the crossing number of G, which, by the way, I think I'm gonna denote that Cn of G, the crossing number of G. I don't think I used that notation in this handout, but that's all right. Is the fewest possible. It is just the fewest possible number of crossings. It's the fewest possible number of crossings among edges of G. So if you were to try to draw the graph of G, drawing it with as few crossings as possible, this is the definition of the crossing number of the graph. And so just, as a note, I guess, right, you could, I think this is pretty much just clear. The crossing number of a graph would be 0. Meaning you're drawing it with no crossing edges at all. That's literally what it means for G to be planar. Okay, so if G is planar, then the crossing number is going to be 0, right? So what this group work problem says on number 2 here is, so I'll just go to group work number 11, problem 2A. What it is saying there on that group work problem, it says show, so we'll just do this as an example, show that the crossing number of K5 is 1. And also for K33, but let's start with K5. Okay, so K5, let me just draw that graph for you. I think you all know what this is. This is just going to be like a pentagon with a star inside of it. This is our K5 graph, just to have a picture of it. And I'll try to make my vertices a little more pronounced here. So there's your K5 graph. And you can see that as it's drawn right now, there are tons of crossing edges. Now we know that this K5 is not planar. You may remember we talked about this on Tuesday. It was not planar. Ultimately, that became part of Kuratowski's theorem that if you have a non-planar graph, right, it's going to either have like a K5 inside of it or a K33, homeomorphic to K5 or K33. So this is not planar. So the smallest possible crossing number would be 1. If you could draw it with only one crossing edge, that would be game over, right? That would basically prove it because you've done the best you could. Can we do that here? Just to see if we can do it. I'm going to leave the pentagon the way it was. I might have even shown you this before. So I just leave the pentagon the way it is, and then What I might do is take the two vertices, sorry, the two edges that are coming down from the top of the pentagon and just redraw them on the outside. Redraw both of them on the outside like so, okay? And then for the other edges, we'll just leave them the same. So we would have these edges here. Okay, and you see that there is still one crossing in the graph, right? We all can see that, I think. So this is the best we can do. We know we can't do better. We know this graph, so I'll just recall that K5 is non-planar. So the crossing number of K5 is at least 1. It can't be planar. So the crossing number is at least 1. And then the picture shows you that the crossing number is at most 1, right? That's how you put this together. So the picture shows that the crossing number is at most 1. You've already got Kuratowski's theorem that says that it is at least 1. And so thus, putting the two things together, the crossing number of K5 is actually equal to 1. It's actually equal to 1. Okay. I'm sorry?
Proof by picture.
It is half done by picture. So I actually have in the group work there, I have a summary at the very bottom of the group work, which says that in order to show that the crossing number is n, you must do two things. The first one is the picture. Show that a graph in which, show a picture of the graph in which you have the right number of crossings, right? And then you have to prove that you cannot have done better than that. That's the second part of it. Okay, Fernando?
How do we do it? Like if we want it, like we can't do it so that it's like so like see edge. Like how do you go like with two? Because then like in the sense you would be then showing like, oh, I drew the picture with 2, but then how do you know you can draw with 1?
So if you don't know what the crossing number is, you mean?
Right, so you're guaranteed to know that it will be planar by using one of the facts that we have.
So if you draw it with 2 crossings, that's not good enough.
Right, so then does that then mean that like?
That means you better get smart about it fast and figure out how to draw it a different way, right? You know, it's like, I'm not drawing my edges very well here. I better try again. You know what I mean?
So then we can always do it so that it's actually exactly 1.
Yeah, you should be able to hit the exact right number. You should be able,
Well,
yes, you should
So
be
it'll always
able.
be 1
Hmm?
then? Will it always be 1?
The crossing? No,
Because
no,
it'd be
no.
like 2, 3, right?
No, let's do another example. So I think if I do another example, I might answer your question.
Yeah.
I'm not sure if I'm understanding your question. Let's actually look at part B of this problem. So of this group work, so problem 2B. Right, what this one is saying is this is gonna ask us to show that the crossing number of K6 is equal to 3. All right, so the first thing I would probably do is just draw the K6 graph. So this is gonna take a little bit of, I would give yourself plenty of room here, so we have enough space to draw the whole picture. Every single vertex should have degree 5. All right, so just draw all of the possible edges here to everything. And I'll give you guys a minute to catch up as well. Just draw all of these in here. And I think that's going to be the picture. So that is a lot of crossing edges in the middle. That's $1 billion for every bridge. That's going to cost a city a fortune to draw the highways like that.
Is that what the Pentagon's so expensive?
So exactly, we're gonna try to figure out how to draw it without so many crossing edges. So the first thing we would like to do is figure out how to draw this with only 3 crossings. We know we're not going to do better than that. So we're gonna live with that that knowledge. So let's just start moving some edges to the outside, kind of like what we did here. It's a reasonable strategy. So I'm gonna, I don't know how you guys want to take notes on this, but I'm going to erase with my finger. So I'm gonna like take this edge right here. You could maybe just dot that edge if you wanted to, or you could just fully erase it and just draw it out here. Okay. So that's gonna remove quite a few crossings. Now, what else could I do? Maybe I could take this vertical edge and move that one also to the outside. So that's this edge right here. Okay, and then maybe I could take this edge here, which is kind of on the lower part of this picture, and let's try to move that one to the outside as well. And am I getting there? Kind of. Let's take this horizontal edge and move it to the outside. I know that when I remove it from here and I want to draw it going to the edges, I know I'm gonna have to have a crossing. So I'm gonna accept that because I know that I'm gonna not get down to 0. So I'm gonna come way over here and just draw this edge like so. So I've created a crossing there. I have to live with that. Okay. And let's try to do the similar thing with some of these other crossings. So this edge is now good. This one here has 2 crossings on it. I wonder if I could like try to move this one anywhere else. Well, how many crossings do I have? I have 1, 2, 3. I'm still at 4, right? I'm almost there. So I just need to move one more edge.
Oh, the diagonal one. Yeah.
This one here.
Yeah.
Okay, so I'm gonna take that one out, and where am I gonna move it? This is the fun part, is just figuring out, so I wanna connect these two with only one crossing though. Can I do that? I don't think so. So I had this one here. Yeah. What if sorry, this one that I'm sorry, I'm struggling a little bit to figure this out. What if I actually, let's pull this one way up here. Like that. I still have that one crossing there, but then can I still have this, and this.
I started with like 4 together and then having an X.
Uh-huh. So you've already got it. Do you want to come draw it? Yeah, I'm not quite getting it. Probably because I started off, I moved a bunch of edges to the outside, probably not in an optimal way. Yeah, so why don't you show us what you did? Be very helpful. Bail me out here. We have one cross in the middle, but that's okay. Every vertex has to have degree 5. Okay, so that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, I think that's going to work. I think that works really well. All right, great job, Julie. Let's give her a hand. That was very, very helpful. Take the blue graph, forget my stuff. Okay, but I only have 2 minutes and I need to explain the real part I want to get to is not so much that, because that's just drawing the picture. I want to discuss how do I know that I cannot, how do I prove that I cannot do better than that? How do I prove that I couldn't have done it with 2? So this picture shows that the crossing number of K6 is at most 3. But how do I know that I could not have done it with less than 3? So the idea behind that is to use the edge inequalities. There's even a hint here. So to prove that the crossing number of K6 is at least 3, right? Let's count the edges and the vertices. Of course, there's 6 vertices here. The number of edges in K6 is actually 6 choose 2, which is 15. Right? And so if we look at, 3n minus 6 is only 12. Okay, so what I'm gonna do is I'm gonna imagine, by way of contradiction, what if the crossing number was only 2? Okay, I want to prove it's at least 3. If the crossing number of K6 was at most 2, so this is by way of contradiction. Just want to make sure everybody can do this part of the reasoning. That would mean that if I removed 2, so I could look at the 2 crossings. I could say, all right, I'm going to remove one of the edges that's causing that crossing. That would eliminate that crossing. Like if I remove this diagonal edge, then that crossing is gone, right? So if the crossing number is at most 2, then I should be able to remove 2 edges from the graph and be left with a planar graph, right? So if the crossing number is at least 2, then we can remove 2 edges from the graph and have a planar graph. Okay, but the thing is, if we remove 2 edges, how many edges do we have? Here's how many edges we started with. If we remove 2 edges, how many do we have? 13, right? Well, that's still too many for this 3n minus 6 thing, right? So now we would have, I'll just finish it over here. We would have 13 edges, right? And G should, not G, I guess K6, well, I'll call it G because it's not K6 anymore. I'll just say the graph. The graph should be planar. Because you've removed 2 edges that were both causing the crossings. Every time you remove one of those edges that participates in that crossing, you get rid of that crossing. So it should now be planar. However, 13 is not less than or equal to 3n minus 6, which is still 12. Okay, so that's a contradiction. So that's how you do it. Okay, so that's how you do it. If by way of contradiction, if the crossing number was less than what you were able to draw here, then you should be able to remove some of those edges that are involved in that crossing and get to a planar graph. That's kind of how you would do an argument like that. There are, on this homework assignment, which is still here, guys, question 3, again, I'm not assigning it after all, but I would recommend these problems that are here, give them a try. It's asking what is the crossing numbers of those 4 graphs. I will post the solutions so you can practice that on your own, but it's basically this is the idea. All right, guys, thank you so much. I assume I'll see a few of you between now and the weekend. If not, be safe. Have a wonderful Thanksgiving, and I will see you in December.
So, like,
Walking down.